Somewhere in the frozen silence beyond our blue planet, a moon circles a giant. It does not glow with the golden warmth of a star, nor shimmer with an Earth-like promise. It is cold. It is dark. And yet, it might be alive. What if the most habitable places in the cosmos are not planets at all? What if life, strange, ancient, perhaps even intelligent, has been hiding not in the glittering embrace of suns, but in the cold shadows of distant moons? For decades, our eyes have turned to planets, Mars, Venus, distant Earth-like exoplanets in the habitable zone of faraway stars. We've imagined alien forests swaying in strange winds, oceans stretching across worlds just like ours. But what if the real secret lies elsewhere? What if we've been looking in the wrong direction? There are more moons in our solar system than planets, and many of them aren't barren chunks of rock. They're dynamic, complex, and eerily active. Some have atmospheres, some have oceans, some show chemical hints that whisper of biology, and some are heated not by sunlight, but by forces deep and unseen. Europa, one of Jupiter's largest moons, looks like a smooth marble cracked with brown veins. Its surface is ice, hard, frigid, dazzling, but beneath that frozen shell lies something extraordinary. A global ocean, deeper than Earth's deepest trenches, stretches for miles beneath the ice. That ocean contains more water than all of Earth's oceans combined. It is warmed not by the distant sun, but by tidal heating, an invisible hand squeezing Europa as it orbits Jupiter, creating friction and heat in its core. It's this same process that allows volcanic activity on moons like Io, despite their great distance from the sun. But Europa is different. That warmth, trapped beneath a frozen crust, creates a liquid sea. And where there is water, especially warm water, there is potential for life. In 2012, the Hubble Space Telescope detected plumes of water vapor erupting from Europa's surface, geysers blasting into space. Like a cry from the deep, these plumes might offer us a chance to sample its hidden ocean without ever drilling through the ice. NASA's upcoming Europa Clipper mission will orbit this enigmatic moon, searching for signs, chemistry, heat, organics that hint at something living in that vast subsurface ocean. Then there's Enceladus, a tiny moon of Saturn, so small it should be dead, and yet it isn't. It spews jets of water vapor, ice particles, and complex organic molecules from deep fissures near its south pole. These geysers form a shimmering halo around the moon and even feed Saturn's E-ring. But where is all that water coming from? Beneath its icy crust lies yet another global ocean, warmed by tidal forces. In 2017, the Cassini spacecraft detected hydrogen in those plumes, an ingredient that, when mixed with carbon dioxide and heat, could feed microbial life through a process called methanogenesis. On Earth, this very process sustains life in the darkest parts of the ocean, around hydrothermal vents where sunlight never reaches.
If it can happen here, why not there? Titan, Saturn's largest moon, is even stranger. It's the only moon in the solar system with a thick atmosphere, a golden haze of nitrogen and methane. On Titan, rivers flow, lakes ripple, but they are not made of water. They're composed of liquid methane and ethane, chilled to hundreds of degrees below zero. Rain falls from thick clouds onto a frozen landscape that mirrors Earth in structure, but not in substance. Could life exist in such alien chemistry? Scientists believe it's possible. Not life as we know it, not water-based cells, but life that breathes methane, that swims in hydrocarbons, that thinks in a biochemistry utterly foreign to our own. Some researchers have even proposed models for such life. Cell membranes made from acrylonitrile, capable of functioning in liquid methane, resistant to cold, and stable in Titan's unique environment. And yet, Titan might not be limited to just exotic life. Some models suggest an internal ocean of water and ammonia beneath its surface, perhaps a second stage, a dual biosphere of sorts. Methane-based life above, water-based life below. Two alien ecosystems coexisting on a single moon. What makes moons like Europa, Enceladus, and Titan so compelling isn't just their water or chemistry or heat, it's how they challenge our assumptions about habitability. We used to believe that life needed a planet in the Goldilocks zone, not too hot, not too cold, just right. But these moons orbit gas giants far from the sun, in realms we once thought were frozen and dead. And yet they are alive with geological activity, rich in chemicals, bathed in energy, not from stars, but from gravity itself. Tidal heating, caused by the immense gravitational pull of giant planets, stretches and squeezes their moons, generating friction and warmth from within. That heat can melt ice into oceans, drive chemical reactions, and create stable environments for life. In fact, moons may be more stable than planets. Their orbits are often less eccentric, their environments less volatile. They may be protected by the magnetic fields of their host planets, shielding them from deadly radiation and cosmic rays. And consider this: in a galaxy where gas giants are common, exomoons might vastly outnumber Earth-like planets. Each one could be a hidden world orbiting silently, cloaked in shadow, harboring life we've never imagined. The Kepler Space Telescope has revealed thousands of exoplanets, but it has also hinted at something more elusive: exomoons. One candidate, Kepler 1625bi, could be the first moon discovered beyond our solar system. If confirmed, it's a Neptune-sized moon orbiting a Jupiter-sized planet in the habitable zone of its star. A moon that massive could potentially have its own atmosphere, its own weather, its own ecosystem, perhaps even its own moonlets.
But how do we find them? Exomoons are faint. They don't shine like stars. They don't eclipse like planets. They whisper instead of shout. But new techniques like transit timing variations and advanced light curve analysis are bringing them within reach. The James Webb Space Telescope, with its precision and power, may finally open the door to their secrets. And what secrets they might hold. Imagine a moon with an ocean 10 miles deep, teeming with alien microbes feeding on sulfur vents. Imagine a skyless world locked beneath ice, its biosphere completely cut off from the outside universe. A planetless moon, wandering in darkness, orbiting a rogue planet adrift between stars, yet still warm, still alive. Life doesn't need sunlight. It needs chemistry, liquid, and energy. And moons have all three. We've searched the planets, scanned their deserts, drilled their soil, but the silence lingers. Mars may have once held life, but today it is dry and still. Venus may have once been Earth's twin, but now it is a furnace of acid and fire. Earth remains the only known cradle of life. But perhaps, in our cosmic quest, we have been blind to the truth. Perhaps the real cradles are smaller, colder, quieter. In the shadow of Saturn, under the grip of Jupiter, orbiting nameless giants in distant systems, moons may outnumber planets, outlast them, and outlive them. They may be the keepers of life's second genesis, not just oases in space, but laboratories of alternate biology, sanctuaries of evolution, maybe even homes. What lies beneath Europa's ice? What swims in Titan's dark lakes? What ancient echo rises with the vapor from Enceladus? We don't know, not yet, but we are watching, we are listening, and soon we may go. Because in the end, the question may not be whether we are alone in the universe, but whether we have been looking in the wrong places all along. Could life be hiding in the shadows of the moons? And if so, what kind of life is waiting for us to find it?